Electrostatic arc-liberated water dissociation as a source of excess propulsive energy. Theoretical framework, mathematical derivation, and extended applications in space, industrial, underwater, and high-energy beam systems. Chris D. Seeley. Independent researcher, New Brunswick, Canada. Correspondence. Related patent, Howard, T.D. and Seeley, C. Systems and Methods for Projectile Propulsion. U.S. Patent Number 11,674,769 B2. Received, 2024. Accepted, published. Abstract. This paper presents a rigorous theoretical and mathematical analysis of the excess energy phenomenon observed in electrostatic arc-liberated water explosions, as documented by Grano et al. At the Cavendish Laboratory, University of Cambridge. When a high-current electric arc is passed through a small volume of water via rapid capacitive discharge, the resulting fog cloud expansion yields measurable kinetic energy exceeding the electrical energy input, attributable primarily to the electrodynamic liberation of hydrogen bond energy stored within the bulk water structure. The present work derives governing equations for capacitive energy storage, arc discharge dynamics, fog cloud expansion kinematics, and hydrogen bond dissociation enthalpy. The paper then substantially extends the theoretical treatment to a broad portfolio of advanced applications: variable explosive discharge in submerged explosion forming and explosive fusion welding, variable field underwater countermeasures, low-energy high-frequency pulsed non-lethal applications, the formation of a directed hydrogen lance, and pulsed microwave amplification by stimulated emission of radiation configurations for precision material processing. Current and future space propulsion architectures are examined, including in situ water-sourced propulsion in orbital, lunar, and deep space environments. Together, these analyses establish a unified theoretical foundation for a new class of electrohydrodynamic energy conversion systems with transformative potential across defense, manufacturing, space exploration, and precision science. Keywords: water arc explosion, electrostatic discharge, hydrogen bond energy, excess energy, capacitive propulsion, explosive forming, explosive welding, underwater countermeasures, hydrogen lance, pulsed maser, space propulsion, Grano effect, electrohydrodynamics. 1. Introduction. Conventional propulsion and energy conversion systems operate within thermodynamic frameworks wherein output kinetic or mechanical energy is bounded by the chemical potential or stored electrical energy of the source material. The energy density of state-of-the-art chemical propellants and capacitive storage devices imposes hard engineering ceilings on achievable projectile velocities, forming pressures, and beam powers in virtually every domain from firearms to manufacturing to space propulsion. In 2000, Grano et al. Reported at the Cavendish Laboratory, University of Cambridge, that the kinetic energy of a dense fog cloud generated by an electrostatic arc-liberated water explosion can substantially exceed the electrical energy delivered to the arc. The authors attributed this excess to the liberation of hydrogen bond energy stored in the molecular lattice of liquid water, driven by the electrodynamic forces of the high-current arc plasma. The fog droplets were observed to expand at supersonic velocities exceeding 350 meters per second, with kinetic energy consistent with liberation of energy equivalent to the latent heat of vaporization, approximately 2,200 J per kilogram, without significant thermal input to the bulk water. The present paper serves two principal purposes. First, it develops the complete mathematical framework for the water arc explosion excess energy mechanism, extending and formalizing the treatment initiated in earlier work associated with U.S. Patent Number 11,674,769 B2. Second, and more substantially, it extends this framework to a wide array of advanced applications that have not previously been treated in the literature: variable explosive discharge forming and fusion welding in submerged environments, variable field underwater countermeasures, pulsed non-lethal deterrent systems, the directed hydrogen lance, pulsed maser configurations for precision material processing, and both near-term and far-term space propulsion architectures. Each application domain is analyzed within the Unified Electrohydrodynamic Energy Conversion Framework established in Section 3. 2. Theoretical background. 2.1 The Grano water arc explosion phenomenon. A water arc explosion is initiated when a sufficiently high current electric arc is passed through a small volume of water. The electric arc does not significantly heat the bulk water. The temperature of the resulting fog cloud is reported to be only marginally above ambient. This observation eliminates conventional thermal vaporization as the primary energy mechanism and redirects theoretical attention toward electrodynamic and thermochemical explanations. Liquid water is a hydrogen-bonded network wherein each water molecule participates in approximately 3.4 hydrogen bonds on average at room temperature, with an average bond energy of approximately 20 kJ per mole. Grano et al. Proposed that the arc plasma exerts electrodynamic Lorentz-type forces on the current-carrying fluid elements sufficient to overcome cohesive surface tension and hydrogen bonding forces, fragmenting the bulk liquid explosively into a dense fog of submicron to micron scale droplets. 2.2 Energy Budget Overview. The total energy balance of the arc explosion event is expressed as where E is the total mechanical energy of the expanding fog cloud. E is the electrical energy delivered to the arc from the capacitive discharge, E is the liberated hydrogen bond energy, and E represents thermal, acoustic, and electromagnetic radiation losses. The excess energy condition E greater than E is explained thermodynamically by the contribution of E. 3. Mathematical derivation. 3.1 Capacitive energy storage. The charge stored in a capacitor bank is, and the stored electrical energy is. For n capacitors in parallel, C equals sigma C. As a reference case, C equals 100,000 microfarads, V equals 100 V gives E equals 500 J. 3.2 Discharge pulse dynamics. The LC discharge circuit obeys peak current and pulse period in the undamped regime. Arc energy deposition over the pulse. 3.3 Hydrogen bond energy liberation. Specific hydrogen bond energy per unit mass of water. Total liberated hydrogen bond energy for water mass m with liberation efficiency eta. 3.4 Fog cloud kinematics and propulsive force. The impulse delivered to a projectile of mass m. Propulsive efficiency. For a 1 gram water mass producing fog at 350 meters per second, E equals 1/2 times 10 cubed times 350 squared approximately equals 61.25 J, yielding a ratio E approximately equals 6.1 for E equals 10 J, directly demonstrating the excess energy condition. 3.5 Electrodynamic Lorentz force and pinch effect. The Lorentz body force per unit volume on the arc plasma. Azimuthal magnetic field at arc radius r. Inward radial pinch force per unit arc length. For I equals 5000 A, F, L approximately equals 2.5 N per meter. Over L equals 1 centimeter and T equals 1 microsecond, the impulse is sufficient to initiate water lattice fragmentation as observed by Grano et al. 4. Application to capacitive discharge propulsion. The propulsion system disclosed in U.S. Patent Number 11,674,769 B2 implements the water arc explosion mechanism in a compact, self-contained projectile propulsion architecture comprising a propulsion chamber housing both a water-containing propulsive charge and a projectile, a capacitor bank discharge subsystem, conductive pathways delivering the pulse to arc electrodes, and a barrel in fluid communication with the chamber. For C equals 100,000 microfarads and V equals 100 volts, E equals 500 J even at eta equals 0.5, E equals 250 J, which is 49% greater than the approximately 168 J produced by a conventional 0.22 caliber round. The use of superconducting conductive pathways minimizes resistive losses in equation, maximizing the fraction of stored energy delivered to the arc. 5. Space propulsion and orbital applications. 5.1 Motivation for water-based space propulsion. Water is among the most abundant volatile compounds in the solar system, present as ice in permanently shadowed lunar craters, on the Martian polar caps, in cometary nuclei, and in the subsurface oceans of Europa, Enceladus, and other icy moons. As in situ resource utilization architectures mature, the ability to convert locally harvested water directly into propulsive energy, without the mass penalty of carrying conventional propellants from Earth, represents a paradigm shift in space mission design. The Arc-Liberated water explosion mechanism offers precisely this capability. Water serves simultaneously as propellant mass, hydrogen bond energy reservoir, and reaction medium. 5.2 Specific impulse analysis for water arc space propulsion. The specific impulse I of a propulsion system is defined as where F is the thrust force, m is the propellant mass flow rate in kg per second, and g0 equals 9.81 meters per square second is the standard gravitational acceleration. For a pulsed system operating at repetition rate f, each pulse ejecting water mass m at effective exhaust velocity v. Therefore, with v equals 350 meters per second, I approximately equals 35.7 s. This is modest compared to chemical rockets but substantially exceeds cold gas thrusters and is competitive with resisto-jet systems. More significantly, the energy input per pulse E is recyclable via onboard photovoltaic or nuclear power sources, and the propellant is harvestable in situ. With optimized electrode geometry and higher discharge voltages, V values in excess of 1000 meters per second are theoretically attainable, yielding I greater than 100 s. 5.3 Variable thrust and precision attitude control. A key advantage of the capacitive discharge architecture is precise programmable control of the discharge energy per pulse via adjustment of V and C. From equation, E scales as VCap2, enabling fine-grained thrust authority across several orders of magnitude without moving parts or throttle valves. For attitude control thrusters, pulse repetition frequency F provides additional control authority. A multi-axis thruster array, each independently addressed by its own discharge circuit, enables full 6° of freedom attitude and translational control. The absence of liquid propellant feed lines, combustion chambers, and nozzle cooling requirements dramatically simplifies the mechanical architecture relative to conventional hydrazine or bipropellant systems. 5.4 Deep space and icy moon surface applications. On icy moon surfaces such as Europa or Enceladus, freely available surface or near subsurface water ice can be melted and fed to the discharge chamber via a simple resistive heating element, enabling in situ replenishment of the propellant supply. The total energy budget for such a mission segment is governed by where n is the total number of discharge pulses required for the mission segment. E equals m times L is the energy required to melt the required water mass, and E accounts for conductive and radiative thermal losses in the feed system. For a CubeSat-class spacecraft requiring a total delta versus of 10 meters per second with dry mass m equals 2 kilograms, the Tsiolkovsky rocket equation gives at I equals 35.7 s and delta V equals 10 meters per second, the propellant mass fraction is approximately 2.9%, requiring only approximately 60 grams of water, an entirely practical proposition for an ISRU-capable small satellite. 5.5 Vacuum operation considerations. Operation of the water arc discharge system in vacuum requires containment of the propellant within the discharge chamber up to the moment of firing to prevent evaporation losses. The chamber geometry disclosed in U.S. Patent No. 11,674,769 B2 is inherently sealed prior to discharge. In vacuum, the absence of ambient atmospheric back pressure increases the effective expansion velocity of the fog cloud, potentially improving I relative to atmospheric operation. The arc initiation physics are unaffected by ambient pressure, as the arc forms within the liquid water medium rather than in the surrounding gas phase. Thermal management of the capacitor. Bank in the space environment requires radiative cooling design, as convective cooling is unavailable in vacuum. 6. Variable explosive discharge in submerged explosion forming and fusion welding. 6.1 Submerged explosion forming. Explosive forming is an established manufacturing process in which the pressure wave generated by a detonation event drives a metal workpiece against a die, producing complex geometries with exceptional surface finish and dimensional accuracy. Conventional explosive forming employs chemical high explosives such as PETN or RDX, which are single-use, hazardous, and difficult to control with precision. The water arc explosion mechanism provides a direct analog to chemical explosive forming but with programmable, repeatable, and precisely variable energy delivery. The peak pressure P generated in a submerged explosion at standoff distance d from an energy release E in a volume 5 is approximated by the similarity scaling relation, where K1 and alpha are empirically determined scaling constants dependent on the explosion medium. R0 is a reference radius, and the exponent 1/3 reflects the cube root scaling of explosive pressure with energy density. By varying V, the peak forming pressure can be tuned continuously across a wide dynamic range without any physical change to the tooling or setup. This represents a fundamental advance over chemical explosive forming, where energy adjustment requires substitution of different explosive charges. The impulse per unit area I delivered to the workpiece surface, where the pressure time history P is shaped by the capacitive discharge waveform, the arc geometry, and the acoustic impedance of the water medium. Multi-pulse sequences can be programmed to deliver shaped pressure profiles, enabling forming of complex contours and gradual work hardening control impossible with single-shot chemical explosives. 6.2 Underwater explosive fusion welding. Explosive welding is a solid-state joining process in which the impact velocity and pressure at the weld interface are sufficient to produce a jetting phenomenon that clears native oxide films and brings virgin metal surfaces into intimate atomic contact, forming a metallurgical bond without bulk melting. The process is governed by the interface collision velocity v and the dynamic angle beta between the flyer plate and the base plate at the moment of collision. The welding window, the range of v and beta values that produce sound welds, is material-specific and well-characterized. The critical collision velocity for welding is where sigma is the dynamic yield strength of the softer material, rho is its density, and k is a dimensionless constant. The flyer plate velocity versus must satisfy v is greater than or equal to v, sin. In the water arc explosive welding configuration, the discharge chamber is positioned between the flyer plate and a water buffer volume. The arc explosion pressure wave accelerates the flyer plate to the required collision velocity. The key design equation relating discharge energy to flyer plate velocity is derived from impulse momentum, where A is the flyer plate area and m is its mass. Substituting equations and v is directly controllable via v. Unlike conventional explosive welding, the process is repeatable, the discharge energy is precisely reproducible to within the charging accuracy of the capacitor bank, and no explosive licenses or safety exclusion zones are required. Dissimilar metal much less than combinations, aluminium to titanium, copper to stainless steel, refractory metal cladding, all feasible with conventional EXW, are equally accessible via water arc explosive welding. Submerged operation of the entire assembly eliminates the need for a buffer layer between the explosive and the flyer plate, simplifies fixturing, and provides natural pressure confinement. For offshore pipeline repair and underwater structural joining applications, the inherent aquatic operating environment of the water arc mechanism is a direct advantage. 7. Variable discharge field underwater countermeasures. 7.1 Operating principle. Conventional naval mines and underwater explosive countermeasures rely on single-use chemical explosive charges initiated by contact, magnetic, acoustic, or pressure fusing. The water arc explosion mechanism enables a fundamentally different class of underwater countermeasure. A reusable, electronically programmable device capable of generating variable intensity pressure pulses on demand, without chemical explosives, detonators, or single-use components. The device comprises a sealed pressure housing containing a water arc discharge chamber, a capacitor bank, a power source, and a programmable firing controller. The discharge energy E is set by the charging voltage V according to equation. The resulting pressure field in the surrounding water medium is governed by the spherical wave propagation equation. where r is the distance from the source, P0 is the peak pressure at reference radius r0, C0 approximately equals 1,480 meters per second is the speed of sound in water, and F is the normalized pressure waveform determined by the discharge pulse shape. The 1r geometric spreading law applies in the far field, while near-field nonlinear effects dominate within the cavitation radius r. 7.2 Variable field control and graduated response. The variable discharge capability enables graduated response. A low-energy pulse at high repetition frequency can generate an acoustic deterrent field sufficient to warn or redirect marine mammals or divers. An intermediate energy setting produces a concussive pressure field capable of disorienting or disabling unprotected personnel or light underwater vehicles. And a maximum energy discharge produces a destructive pressure pulse comparable to a conventional mine. The energy scaling follows directly from equation. A typical design with C equals 10F and V adjustable from 10 volts to 1,000 V spans an energy range of 500 J to 5 megajoules, covering the full spectrum from acoustic deterrence to destructive lethality within a single device, selectable in real time by the firing controller. 7.3 Multi-pulse directed pressure array. An array of discharge chambers positioned in a geometric arrangement can produce a directed pressure beam via constructive interference of the individual pressure pulses. For an array of N chambers fired with inter-element delay delta T, the pressure field on the beam axis is where r is the distance from the ith element and tau equals r, C0 plus delta T is the time delay for beam steering. This phased array architecture enables electronic beam steering without mechanical articulation, with beam direction controlled entirely by the firing delay pattern programmed into the firing controller. 8. Low-energy high-frequency pulsed non-lethal applications and the hydrogen lance. 8.1 High-frequency pulsed non-lethal deterrent. At low discharge energies and high pulse repetition frequencies, the water arc mechanism generates a sustained acoustic and hydrodynamic disturbance field rather than a single destructive impulse. The time average power delivered to the medium is for E equals 1 J per pulse and F equals 100 Hz, P equals 100 W. The resulting acoustic pressure field at 1 meter standoff, assuming omnidirectional radiation, is where Z0 equals rho C0 approximately equals 1.48 times 10 to the power of 6 pas per meter is the acoustic impedance of water. At r equals 1 meter, P approximately equals 0.49 times 10 cubed Pa approximately equals 0.49 kilopascals, corresponding to approximately 148 decibels SPL in water. This exceeds the pain threshold for unprotected divers and is sufficient to cause disorientation and involuntary withdrawal. The device is non-lethal at operational ranges but effective as a perimeter deterrent, area denial tool, or crowd control device in aquatic environments. 8.2 The directed hydrogen lance. The directed hydrogen lance is a novel application mode in which the high-frequency, high repetition rate pulsed water arc discharge is configured not to disperse the fog cloud omnidirectionally but to direct it as a coherent, sustained, high-velocity stream along a defined axis. This is achieved by confining the discharge chamber with a convergent-divergent nozzle geometry that collimates the expanding fog cloud into a directed jet. Analogous in principle to the thrust nozzle of a chemical rocket but operating at much lower temperatures. The exit velocity of the directed hydrogen jet is governed by the isentropic nozzle expansion equations applied to the fog gas mixture. Treating the fog cloud as a compressible two-phase flow with effective ratio of specific heats gamma and stagnation pressure P0 in the discharge chamber. For a high-energy pulse sequence, V can approach or exceed 1,000 meters per second. The jet carries both the kinetic energy of the accelerated fog droplets and the chemical reducing potential of dissociated hydrogen, providing simultaneous mechanical cutting and chemical surface activation, of relevance to applications such as high-pressure water jet cutting, surface cleaning, and de-icing. At lower energies, the pulsed hydrogen lance operating at body-safe acoustic power levels and pulse frequencies in the range 1 to 10 Hz produces a tactile percussive effect detectable at standoff distances up to several meters in air. Deployable as a non-contact crowd deterrent or search and rescue signaling device. 9. Pulsed maser for precision material processing. 9.1 Physical basis, water arc excitation of microwave emission. A microwave amplification by stimulated emission of radiation device produces coherent microwave radiation via population inversion in a suitable gain medium. Conventional maser systems employ ammonia, hydrogen, or solid-state gain media excited by optical pumping or electron beams. The present analysis proposes a novel water arc excitation scheme in which the rapidly expanding fog cloud, comprising highly energized, partially dissociated water molecules, hydroxyl radicals, and atomic hydrogen, constitutes a transiently inverted population suitable for maser action. The rotational energy levels of the hydroxyl radical are well characterized. With the ground state pi3, 2J equals 3/2 hyperfine transition at 1667.359 MHz and the satellite transitions at 1612 and 1720 MHz being among the strongest astrophysical maser lines known. The water arc explosion produces O, in abundance via thermal and electrodynamic dissociation of hydrogen oxide. If the discharge chamber is positioned within a microwave resonant cavity tuned to one of these O transition frequencies, the population inverted radical ensemble may produce stimulated emission. 9.2 Resonant cavity design and gain medium analysis. The resonant cavity must support the target maser frequency nu0 with quality factor Q sufficient to sustain oscillation above the threshold gain condition. The threshold gain coefficient G for maser oscillation in a cavity of length L and mirror reflectivities R1, R2 is where alpha represents cavity distributed losses. The small signal gain coefficient of the O medium at line center, where tau is the spontaneous emission lifetime of the inverted transition, delta n is the population inversion density, and dn is the Doppler broadened line width. For the rapidly expanding fog cloud, dn is governed by the thermal and flow velocity distribution, where m equals 2.82 times 10 squared to the power of 6 kg is the O molecular mass and T is the effective rotational temperature. For T equals 500 K, dn approximately equals 4.2 kHz at 1667 MHz, a narrow line width that is favorable for high gain per unit path length. 9.3 Pulsed maser operation and material processing. In pulsed operation, each water arc discharge event produces a transient O population inversion lasting on the order of the collision quench time tau approximately equals, where n is the O number density, sigma is the quenching cross-section, and v tilde operator is the mean thermal velocity. For n approximately equals 10 squared cubed m cubed, tau approximately equals 10 to the power of 7s, sufficient for a microsecond scale maser pulse to build up from noise within a high Q cavity. The peak maser output power scales with E via the O production yield, which is proportional to the arc energy deposited per unit volume. A precise proportionality exists. Precision control of E via V thus directly controls P, enabling the output beam power to be varied over a wide dynamic range with high repeatability. The pulse timing is controlled to nanosecond precision by the electronic firing circuit, enabling synchronization with external targets or process monitoring systems. For material processing applications, the pulsed maser beam is coupled out of the resonant cavity through a partially transmitting output coupler and focused onto the workpiece. At microwave frequencies, the penetration depth delta into a material of electrical conductivity sigma is given by the skin depth formula, where mu is the material permeability and omega equals 2pn0 is the angular frequency. For metals at 1667 MHz, delta is on the order of tens of micrometers, enabling surface heating and ablation with controllable penetration depth. For dielectric materials, Microwave absorption occurs volumetrically via dipole relaxation, enabling through thickness processing with fine spatial resolution determined by the focusing optics. The combination of nanosecond pulse timing, programmable power control, and frequency selectivity enables the pulsed water arc maser to cut, drill, weld, surface treat, or sterilize virtually any material class with precision and control unattainable by conventional laser or plasma arc processing systems. 9.4 Comparison with conventional laser cutting systems. Conventional carbon dioxide laser cutting systems operate at 10.6 micrometers wavelength with wall plug efficiencies of 10 to 20%. High-power fiber lasers operate at 1.06 micrometers with efficiencies up to 40%. In both cases, the beam material interaction is confined to the material surface at optical penetration depths. The pulsed water arc maser system, operating at centimeter wavelengths, offers fundamentally different interaction physics. Volumetric heating of dielectrics, controllable skin depth heating of conductors, and the ability to process materials in water-submerged or steam-rich environments where optical systems are severely degraded by scattering. The maser is also inherently eye-safe at the power levels required for processing operations, in contrast to high-power laser systems which pose severe ocular hazards. 10. Unified Electrohydrodynamic Energy Conversion Framework. The diverse applications described in sections 5 through 9 are unified by the same underlying physics. The controlled, precisely timed, variable energy capacitive discharge into a water medium that liberates hydrogen bond energy as the primary power source, with the resultant fog cloud, pressure wave, or radical plasma serving as the working medium for the specific application. The universal design parameters governing all of these systems are: discharge energy, E equals 1/2 CV cap 2, the master control parameter, directly tunable by adjusting V. Pulse repetition frequency, F, governing time average power, fog cloud density, and acoustic field intensity. Water mass per pulse, M, setting hydrogen bond energy contribution E equals eta times E times M. Electrode geometry, determining arc plasma spatial distribution, pinch force, and directionality of the propulsive or pressure field. Chamber and nozzle geometry, shaping the expansion of the fog cloud or plasma jet to match the application geometry. This parameter set constitutes a complete design space for the entire family of applications, enabling optimization of any specific system through variation of the 5 parameters above within the governing equations developed in Section 3. 11. Discussion. The theoretical framework presented in this paper establishes a unified electrohydrodynamic energy conversion basis for a broad class of systems sharing the water arc explosion mechanism. Several observations warrant emphasis. First, the excess energy mechanism identified by Grano et al. And formalized here in equations and provides a thermodynamic advantage over purely electrical systems that is not subject to the Carnot efficiency limit of heat engines. As the hydrogen bond energy liberation is an isothermal process driven by electrodynamic rather than thermal forces. This makes the mechanism uniquely suited to low-temperature environments such as deep space or cryogenic processing applications. Second, the programmability and repeatability of capacitive discharge energy provides a level of process control in explosive forming, welding, and countermeasure applications that is categorically unavailable with chemical explosives. The ability to tune energy continuously across orders of magnitude within a single device. With pulse-to-pulse repeatability determined by capacitor charging accuracy, transforms what has historically been a single-use, hazardous industrial process into a precision, repeatable manufacturing operation. Third, the hydrogen lance and pulsed maser applications represent genuinely novel physical regimes not previously described in the literature on water arc explosion phenomena. The hydrogen lance leverages the directed kinetic energy of the fog cloud, the pulsed maser leverages the radical chemistry of the arc dissociation products. Both are enabled by the same underlying discharge physics and both benefit from the same programmable energy control architecture. Fourth, the space propulsion applications are particularly compelling in the context of the current trajectory of lunar and planetary exploration. The convergence of ISRU water harvesting technology with the arc-liberated propulsion mechanism described herein offers a path to fully autonomous refueling of spacecraft from in situ resources with no chemical propellant manufacturing infrastructure required. Open experimental questions include precise calorimetric determination of the liberation efficiency eta as a function of discharge parameters, characterization of the O, radical production yield and rotational population distribution as a function of arc energy, measurement of the Maser gain coefficient of arc-produced O, in a resonant cavity, and systematic determination of forming pressure scaling constants K1 and alpha in equation for the water arc explosion source. 12. Conclusions. This paper has presented a comprehensive theoretical and mathematical treatment of the water arc explosion excess energy mechanism and its extension to a broad portfolio of advanced applications. The principal conclusions are as follows. 1. The excess kinetic energy of the arc-initiated fog cloud is attributable to the partial liberation of hydrogen bond energy, with liberation efficiency eta remaining to be precisely characterized experimentally. 2. Space propulsion applications exploiting in situ water resources are theoretically viable at specific impulse values of 35 to 100 plus s, with full 6 degree of freedom attitude control achievable via multi-axis thruster arrays. 3. Submerged explosion forming applications benefit from continuously variable, precisely reproducible forming pressures governed directly by the discharge voltage, eliminating the safety, regulatory, and process control limitations of chemical explosive forming. 4. Underwater explosive fusion welding using the water arc mechanism is mathematically feasible across the collision velocity angle welding window for a broad range of dissimilar metal combinations. 5. Variable field underwater countermeasures spanning acoustic deterrence to destructive lethality are achievable within a single rechargeable, electronically programmable device. 6. High-frequency pulsed non-lethal deterrent systems operating at 100 W average power produce acoustic pressure levels of approximately 148 decibels SPL at 1 meter in water, sufficient for perimeter denial applications. 7. The directed hydrogen lance, formed by nozzle collimation of the pulsed fog cloud, achieves exit velocities approaching 1,000 meters per second and provides simultaneous mechanical cutting and chemical surface activation. 8. A pulsed maser system exploiting the O, radical population inversion produced by water arc dissociation is physically feasible, with gain coefficient governed by equations, enabling precision material processing with capabilities complementary to and in some respects exceeding those of conventional high-power laser systems. These findings collectively establish the water arc explosion mechanism as a foundational technology platform with transformative potential across space exploration, precision manufacturing, defense, and advanced materials processing. Declarations. Competing interests. The author is a co-inventor of U.S. patent number 11,674,769b2, cited herein as prior art. This relationship is declared in the interest of full transparency. Funding. No external funding was received for this work. Data availability. All data supporting the conclusions are derived from the cited references and the mathematical derivations presented herein. References. Grano, P., Grano, N., Hathaway, G., and Hull, R. Arc-liberated chemical energy exceeds electrical input energy. Journal of Plasma Physics, 63, 115-128. Howard, T.D. and Seeley, C. Systems and Methods for Projectile Propulsion. United States Patent Number, US 11,674,769b2. Filed September 30, 2022, issued June 13, 2023. Soper, A.K. The radial distribution functions of water and ice from 220 to 673 K and at pressures up to 400 megapascals. Chemical Physics, 258, 121-137. Suresh, S.J. and Naik, V.M. Hydrogen bond thermodynamic properties of water from dielectric constant data. Journal of Chemical Physics, 113, 9727-9732. Cassie, A.M. Theory of arc rupture. Proceedings of the IEE. Meyer, O. Über die Theorie des Lichtbogenauslöschung. Elektrotechnische Zeitschrift, 64, 645-652. Tsiolkovsky, K.E. The Exploration of Cosmic Space by Means of Reaction Devices. Science Review. Wirtz, J.R. and Larson, W.J. Space Mission Engineering, The New SMAD. Microcosm Press. Crossland, W.A. Explosive Welding, Forming and Compaction. Applied Science Publishers. Elitzer, M. Astronomical Macers. Kluwer Academic Publishers. Grano, N. and Grano, P. Newtonian Electrodynamics and its Applications. Proceedings of the Royal Society of London A. 400, 235-242. Turner, M.J.L. Rocket and Spacecraft Propulsion, Principles, Practice and New Developments. Springer Praxis. Yuriv, A. Quantum Electronics. Wiley. Cole, R.H. Underwater Explosions. Princeton University Press.